On a prior page, we plotted the voltage and the current for the case of an open termination. And on this page, we're going to learn how to plot the voltage and the current on the transmission line for any termination using a diagram known as the crank diagram. Let's write out the expressions for the voltage and the current on the transmission line that we derived before. We will write them as a function of dimensional variable L, which goes from 0 to a positive number as you move away from the load. Now to quickly review, the voltage and the current at the load can be written with the following expressions. So the voltage is equal to V naught plus multiplied by 1 plus gamma. That's the voltage. And the current is V naught plus divided by Z naught multiplied by 1 minus gamma. This is the voltage and the current at the load, where L is equal to 0. Now let's calculate the repetition rate of the term gamma multiplied by e to the minus 2 j beta L. In order to find the repetition rate, we solve the equation 2 beta L is equal to 2 pi, which gives L is equal to lambda over 2. This means, of course, that this term as a vector rotates fully around a circle every half wavelength. Now let's look at the term 1 plus gamma e to the 2 minus j beta L. Basically, the crank diagram allows you to, or it's a plot rather, of this vector as a function of L. So let's go ahead and draw this vector. Begin by drawing the first part of the term, which is 1. Okay, we'll draw 1 as a vector. And then the second part of the term, we are going to define this part as gamma of L. Which is a vector of some magnitude gamma and some angle alpha. Okay, so this is that vector right there and has an angle of alpha from the ordinate. Now let's draw a little circuit diagram with a load impedance ZL and showing that we are moving on the transmission line away from the load impedance to a location of Z, and as Z goes negative, L goes positive. Okay, now as L increases, the vector gamma of L moves counterclockwise, because as L increases, alpha decreases, and it moves in a circle counterclockwise. Okay, now the vector v of z is actually 1 plus gamma of L, so I drew that in green, and the vector I of z is 1 minus gamma of L. Now it's actually v of z is not really this vector, but that vector is the main vector in the expression for v of z. Likewise, the other vector shown is the main vector in the expression for I of z. So you can see that this crank diagram shows you visually how v of z and I of z are moving as a function of L. And it also shows you where the maximum voltage is and where the minimum voltage is on the transmission line. And as we know from before, VisWAR is defined as Vmax divided by Vmin. It's also important to note that both V of z and I of z make a full circle every half wavelength, as we derived before from finding the repetition rate of the term gamma of L. So in summary, the crank diagram gives us a graphical way to find the main terms in the expressions for V of z and I of z. So the term 1 plus gamma times e to the minus 2 j beta L is the main term in the expression for V of z. And we can track this term on a plot using the crank diagram. And likewise, the term 1 minus gamma times e to the minus 2 j beta L is the main term in the expression for I of z, which we can track again using the crank diagram. Therefore, since we can graphically plot both of these terms as the reflection coefficient gamma of L is changing, we can find the expression for the impedance on the transmission line, or voltage divided by the current, for any reflection, gamma, and any load impedance Z of L.